So what we want to do in this video is put into a framework uh, the solving the system of linear equations. That's called linear algebra, and the component of this is what we've really been doing is doing matrix algebra. So okay, let's just set up the framework. So if we're talking about an algebra, we need a set of objects, and they're going to be matrices, objects that look like this. And we have to talk about how to add, subtract, multiply, and divide. So what we're going to do in this video is we'll introduce the matrix and talk about how to add, subtract, and multiply. And then in the next video, we're going to look into how to divide. And then we're going to see how that relates to basically solving a system of linear equations in Gauss-Jordan. Okay, so what we have here, this object, this is the pieces of this algebra. This is a matrix. And what we have, okay, so you could see that what we were doing was basically matrices. And the way you talk about a matrix is think about sitting in a classroom or the theater. You have your rows, so the screen's at the top. You have your row 1, you have your row 2, right? You could have row 3, row 4, etc., etc. And then we have columns. So this would be column 1, and again, column up and down, right? It's a column, so column from left to right. So column 1 and column 2. And again, you could have 3, 4, you could have any number. Okay, so they have this rectangular structure. We say the size of this matrix is a 2 by 2. It's not a 4, you can't multiply, it's a 2 by 2. And that the first number is rows, so you have 2 rows, and we have 2 columns, 2 columns, 2 rows, 2 columns. Okay, now here's another matrix, and what's its size? So notice we have row 1, row 2, row 3, and we have 1 column, 2 columns. So this matrix is size 3 rows by 2 columns. Okay, 3 rows, 2. It should be 2 columns, right? 2 columns. Now here's a special case, and these kind of matrices, these are special matrices. So notice this is 2 rows, 1, 2 rows, and 1 column. Right, rows by columns, and this is a special case. This is called a column vector, and this is going to be these are going to be necessary for doing multiplication. And this is another special case, and this is 1 by 2, 1 row, 2 columns, up and down. Right? 1 column, 2 columns. So this is 1 by 2, and this is called a row vector because it's just a row. So vector is a special case of a matrix. It's just where it's a row or a column. Okay, so these are the building blocks. So again, for the algebra, we want to know how to add and subtract. So here are objects, matrices. I've given 2 matrices. Right, here's a matrix A. Here's a matrix B. I usually think of it as one identity, like a complex number. It's just a number. Okay, it has parts to it, but it's just a complex number. A matrix is the same thing. It's a matrix A, a matrix B. Typically, the notation for matrix is, if it's a matrix, you use a capital letter and boldface. I don't know why. That's how we do it. That's how it's presented in typeset. So matrices are typically given by capital letters and boldface, just so you know it's a matrix. That's just a notation people use. So here we're going to add. Okay, here's subtract. So let's just do this. If I'm going to add, I'm just going to literally substitute in the matrix A and the matrix B. I just literally replace A by its matrix, B by its matrix. Now, this works exactly how you think it's going to work. You're just going to add up likes with likes, right? So we're going to take the minus 5, add it to the 6, and that goes in the top left. Take the 0, add it to the 2, top right. 4, add it to the 2, bottom left. So it goes exactly where you think it goes, right? The pieces all go where they should go. It's actually pretty straightforward. Okay, so there's nothing surprising about adding, subtracting. The minus 5 plus 6 over there is 1. The 0 plus 2 is 2 here. The 4 plus 2 is 6. And the 1 minus 3 is minus 2. So again, there's no surprises. And not surprisingly, subtraction works exactly as you'd expect it to work also. So I substitute in the A and the B. And they go like for like. Again, the minus 5 minus the 6. You just have to be careful with your signs, but that's all. 0 minus the 2. And you get that in the top right. And then the 4 minus the 2 down here. And the 1 minus 3 here. And you just add them together. And you get the minus 5 minus 6 is minus 11. So everything works just as you'd expect it. No surprises. So adding and subtracting is pretty straightforward. Okay. Now multiplying, we're just going to take piece by piece. Oh, final comment. You can see for this to work, the matrices have to be the same size, right? They have to have the same thing so you can add them together or subtract. So they have to be the same size. That's all. Okay, so it's clear of how you do it. So our matrices in this case were both 2 by 2. Okay, so we're going to take multiplication in pieces. First thing we're going to look at is scalar multiplication. And it's scalar because the 3 in this example, I'm taking a matrix, and the 3 here is a scale factor. Okay, now matrices are very common. If you think of your screen or a window in your screen, that's a matrix, right? There's pixels, it has a certain, what is it, something by something. That's exactly what it is. Associated with each pixel would be a color, which would be a number. So your screen is actually represented as a matrix. And if you were to rescale a window, that's what this is. So you're doing 3 times a matrix is just resizing a window. That's all this really is. I'm scaling it up 3 times. So 3 times the matrix. And this works exactly as you might guess. So I just substitute in the matrix A. And it's just going to be 3 times everything in there. So 3 times each entry. 3 times each entry. 3 times each entry. And that's why it's a scale factor, right? You're making everything 3 times as large in here. So if these numbers represented colors, they'd be 3 times as bright or something, brightness. Okay? So the 3 comes up in every entry. I mean, everything gets scaled in the matrix. So each element gets scaled. Each entry gets scaled. And then you just calculate it entry per entry, right? So nothing really surprising here. This is fine. Scalar multiplication is fine. Works pretty normal. And again, now we're going to start off with matrix multiplication. So we have to take it by steps. This is the building block. Okay, this is everything we do, everything more than this is going to be based on this calculation. So make sure you're comfortable with it. And it is pretty straightforward. So this is it. Everything is going to have this in it over and over and over again. Okay? So what you have to check, A times B, here they are. You have to check that they match up in size first off, or you can't do it, and you'll see why in terms of the calculation. Okay, so the first matrix A is a 1 by 3. 1 row, 3 columns, right? And the second matrix is a column vector. It's 3 rows and 1 column. Now what has to happen for this to work, and you'll see why, is the inner numbers have to match, right? We got the green light. The inner numbers have to match for this to work. Okay, so they have to match. And what comes out equals these numbers. So what comes out in this case is going to be a 1 by 1, where the first one comes from there and the second one comes from there. So it's a 1 by 1. Okay, so we're looking for just one thing in here. There's just one number plopped in the middle. This is the basic calculation. So how do we do it? Actually, pretty straightforward. Take this 3 times this 1, put it in there. All right? And then add it to this 1 times this 3, and you get this. Add it to that 1 times that 1. So the first times the first, the second times the second, plus the third times the third. Now, why is it done this way? For everything to work out. You'll see at the end why it works out this way. It has to be defined this way if you want to, well, you'll see. Okay, so it seems a bit strange, but it's done for a reason. But this is your basic calculation. You see why they have to have certain dimensions, sizes to work. And that's it. So it's a pretty straightforward calculation, and we're going to do it over and over again. Okay, so the first one was a 1 by 3, it was a row vector. The second was 3 times 1, it was a column vector. The 3's have to match, and the resulting output is the 1 by 1. Okay, so that's it. That's your basic calculation. Now notice this matrix A is the previous one where we added another row. B is the same. So this is what we had in the last example, just this piece. So you see I'm adding another row here. That's the new feature, and B is exactly the same. So the new feature is, how do we handle it? Well, let's just go through it and see. A times B, there's A, there's B, okay? So this is a 2 by 3, right? That's the new feature. I have 2 rows, and I have 3 columns, right? 2 by 3. Here we have a 3 by 1. 1 row, 2 row, 3 rows, 1 column. Check that the inner numbers match. Green means go, right? Inner numbers match. So we're good. Now the size of the output is going to be the outer numbers. So 2 by 1. That's what's coming out of this. So notice 2 by 1, I just put this in here, is 1 row, 2 rows, all right? 1 row, 2 rows, and 1 column. So that's what we have to fill up. Now, how do I calculate? We need a numbering system. Like if you went to the theater, you went to the ballpark or something, you went to a stadium, you usually use a number for the row and a letter for the column, actually. So this is the first row and the first seat in the first row. First row, first column. Now, this will be more apparent when the matrices are bigger. But it's the first row and it's the first seat, first column. Now, of course, in this case, there's only 1 column, one seat, right? Here's the second row and the first seat in the second row, first column, right? So it's the first row, second row, and it's the first seat in that, right? So usually in like I said, if you go to like, stadiums or something, it would be 2A, 2B, but we just use numbers. Okay, so how do you calculate? Why do you need to know this? Because this tells you how to calculate. So we have to transform this, remember, into the basic calculation that we did in the last example. So what you do here is, I went the wrong way. So your first number, 1, tells you to take the first row, right, it's a row, take the first row from the first matrix. Take that first row from the first matrix. And then multiply it by the first column, now we only have one, of the second matrix. So take the first row from the first matrix, multiply it by the first column of the second matrix. See, the 1 is on the left, so take the matrix on the left, take the first row. The 1 on the right, go to the right matrix and take the first row, first column. And that's a calculation we know how to do. We did this in the last example. So the number that goes in here is what comes out of that. So that's your first row, right? And that's your first column. And now we know how to do this calculation. We just did it. First times first, plus second times second, plus third times third, 8. Now that's a matrix, but we're just going to take that number and plop it right in here. Now how do we do this one? Well, second row from the first matrix, right? Notice it's on the bottom, so we take the second row, right? It's on the bottom over here, bottom over there. And we take the first column here. Now there's only 1 column. And that's your basic calculation. That goes there. So notice that's your first row, your second row from the first matrix. Right? And that's your column, right? From the matrix on the right. Now we know how to do this calculation. The 2 times the 1, first times the first, plus the second times the second, plus the third times the third. And there it is. Now again, that's a matrix, a 1 by 1, but we just want the -4. Take that -4 and stick it right in here. And there you have it. That's it. I put all the calculations on the side there so you can see, but that's it. Now again, you'd probably want to make sure you write something down on tests. If you just write out numbers and you make a mistake, there's no way of checking your work. So you probably want to show some work with this stuff, although, you'll be pretty quick with it. So let's move up the food chain for this example. Now you see what's happening. The matrix A is the same as we had before, but what I've done is I've added another column to B. So this is the most general. You can do anything after this example. This is the more general case. Okay? So A I just substitute in. B I substitute in. Check the sizes. 2 rows by 3 columns. 3 rows by 2 columns. The inner numbers match, right? The inner numbers have to match. And this, what we get out, right, check. What we get out is a 2 by 2. So what we're going to get here is a 2 by 2. So notice I have 4 entries. The 2 comes from the first one, the 2 there, and this 2 comes from the second matrix there. So that's the first row. The 1 is a first row, first column. Right? First row here. First column, so that's the 1, 1. That's, again, going to tell us which ones to pick on the left there. This is the first row, second column. Everything is row column. This one is second row, right? Second row, first column. And this one is second row, second column. Again, those are going to help us to decide how to do the calculation. So let's start here. The 1, 1. First row, first column. First row, second column. Second row, first column. Second row, second column. Okay? Let's start here. So what I'm going to do is I'm going to take the first row from the matrix on the left and multiply it, right? The 1 here tells me to take the first row from the matrix on the left, here. And the 1 here says take the first column on the matrix on the right. Put that here. And that's the calculation we know how to go. So again, the 1 here means that. The 1 there means column there. And we did this calculation already twice, I think. Still equals 8. So that number 8 gets put right here. Now if we go here, again, we take the first row on the left, multiply it now by the second column on the right. You can see the pattern. And if we do that calculation, first times first plus second times second plus third by third, you see, just comes out to be 5, and that goes right here. So you see the basic calculation you just repeat over and over and over again. Now, see if you can do this one. See if you can figure this one out yourself. All right, let me try. So now we take the second row, right? The second row on the left, and we multiply it by the first column on the right. And if we do that calculation, we get -4. Okay, see if you can do this one. So I take the second row on the left, and I do the multiplication against the second row on the right. And we do the standard calculation, and we get 24. And that's it. I wrote down all the calculations here, and that's the end. That's the result. So yeah, there's a lot of computing, but it's pretty straightforward. I mean, it looks, I think, worse than it actually is. So that's the general case. Okay. Now, what we did in this example, this is A times B, this example we just did. Now, this example is B times A. Okay, now look how very different this is than what you would expect with real numbers. First off, notice the sizes are different. B is a 3 by 2 matrix, and A is a 2 by 3. So notice that the output here is a 3 by 3. It's very different. Okay, so see if you can go through and calculate each of the entries here. Pause it and see if you can go through. Okay, so I put in all the calculations here, and I come out with this. Okay, so I put in all the calculations here, and this is what we get. Now notice, just to compare these two, they're very different. Look, A times B is a 2 by 2. B times A is a 3 by 3. So what do we learn from this? you can't, like 2 times 3 equals 3 times 2. But that's not true in general. That's why that's not in an algebra. Notice it matters whether you multiply A times B or B times A, right? It matters. They're completely different. So A times B and B times A clearly are not the same thing. So we're going to have to be aware of that and be careful about that. Okay, so just be aware. A times B is not the same as B times A. Now, why do we go through this trouble? Because we want to put solving these systems of equations. Solving systems of linear equations is a big deal. It's what digital computers do very well. This is a big deal. All the problems we do reduce to this. So we want an efficient way to handle this, and that's where this matrix notation comes into play. We want a way of dealing with this. Okay, so I want to write this as a matrix equation, right? So what we have here is just a system of equations, linear equations. I want to write it as a matrix equation. So notice what we did before. We wrote this is called an augmented matrix, because it's a matrix augmented by the 3, 5, 1 over there. And that gives you your pieces. We were just doing shorthand for what I'm doing here. Notice what I'm going to do is I'm going to take this piece, and I'm going to call it this matrix A. And I'm going to take the piece over here, and that's B. Now, in this notation, vectors you usually write with bold-faced small letters. Now, I wasn't doing that earlier because I don't need to confuse it, and you don't need to be confused about it. But that's generally the convention. A full matrix we write with a capital letter, and the vectors we write with a small letter. So you see, what we were doing before is a special case. It's called augmented matrix. We were really doing this, but still reducing it down even more so. And then X is going to be my X, Y, Z unknowns. That's a vector, meaning, see, it's in boldface, X, Y, Z. So I can represent that system of equations with that shorthand notation, AX equals B. Yeah, big. So that's it. I mean, you always reduce it down to this nice short form, and then just as with a regular equation, the algebra helps. In order to solve this, we'll have our own algebra. And we're going to need to do division and so forth, and that will pick up in the next one. But for the moment, that's how it works. Now, you can see why everything works this way. Let me show you. If you have AX equals B, plug in everything, right? Plug in your A, X, and B. And you'll see how this gives me my system of equations back. So now if you multiply these together, the matrix A is a 3 by 3. The matrix X is a 3 by 1. And you see what I get out of that is a 3 by 1. Right? So it all works out. All the sizes are correct. Now, if I do matrix multiplication, multiply the first row by the column, I get this. First times first plus second times second plus third times third. If I multiply the second row by the column, first column, I get this. And if I multiply the third row by the column, I get this. Okay, so I have this. So now this matrix on the left equals the one on the left, provided the top equals the top, which gives me this. The middle equals the middle, gives me this. And the bottom gives me this. And notice that's what we started out with. So that's how I represent a system of equation in matrix form. Because again, if you're writing computer programs to do it, you don't want to do it for every individual matrix. You want it to be one way that handles it all the time. And we'll talk about that in the next video. But that's the idea. Okay? So what should you get out of this? You should be able to add and subtract and multiply matrices together. Okay, that's what you should be able to do. And you should be able to write the system of linear equations as a matrix equation. That's what you need to do to come out of this and be able to do. Okay, so, well, good luck.